Good morning, good afternoon, good evening. Uh, Please choose the appropriate greeting for the time of day that you're watching this video. We're picking up where we left off last time, jumping right back into section 8.2 and continuing our discussion on hypothesis testing. So just to refresh everyone, in hypothesis testing, we are developing a formalized method of checking whether some preconceived belief we have about a population is consistent with the evidence that we get when taking a sample from that population. So the way we formulated this last time involved 3 steps. Firstly, formulating a null and an alternative hypothesis. Secondly, calculating a test statistic. And then thirdly, evaluating a rejection region. And your conclusion ultimately is based on whether your test statistic is inside the rejection region or outside of the rejection region. The bottom line is, though, that many times in practice, statisticians or other users of statistical methods prefer a different approach than using a rejection region. They prefer using a method known as p-values. So we're going to dig into that a little bit for the next few minutes. And I'll start off by saying the conclusion that you reach using a rejection region and the conclusion that you reach using a p-value will always be the same. So at the end of the day, you're not going to reach different conclusions based on the method that you use. Rejection region is calculated beforehand. You know which values of the test statistic will lead to you rejecting the null hypothesis. On the other hand, with a p-value, this is a probability that we calculate. And the p-value is defined as the probability of obtaining a value for a test statistic at least as contradictory of H0 as the value calculated from the sample data. Now, this is a whole mouthful, but here is how you can think about it. When you are sampling from a population for which the null hypothesis is true, there are plausible values of the test statistic and there are implausible values of the test statistic. That's exactly what our rejection region evaluates. What the p-value does is flip that around, and it quantifies, in some sense, how big the rejection region would be if we constructed a rejection region using our test statistic as reference. And another equivalent way of thinking about it is saying your p-value looks at or evaluates the probability of your test statistic being as extreme or more extreme than what you observed if you were to go and take another random sample. So the p-value ends up being a quantity that gets compared to a pre-specified level of significance. So the way you would construct a rejection region based on a specific value of alpha, your level of significance, in the same way your p-value is going to be compared against that same level alpha. And so since a p-value and a rejection region both rely on the same value of alpha, that is another reason why they're never going to give you contradictory information. So you are going to calculate this p-value or this probability, and I'll talk you through doing that in a moment, but then you're going to compare it against the level alpha. And if in this comparison, your p-value is small, if the p-value is less than alpha, less than or equal to alpha, that will result in you rejecting the null hypothesis. So this is a very informal way of thinking about it. It's not a definition that you would want to use, but one way to help yourself remember is if the p-value is small, there is a small probability that the null hypothesis is true. On the other hand, if the p-value is large, in other words, greater than alpha, we are not going to reject the null hypothesis, because a large p-value means large probability that the null hypothesis is true. Now let's dig a little deeper and figure out exactly how we go about calculating a p-value. And for the time being, I am still going to assume that we are dealing with what we've called case one. In other words, two things are true. We know that the population that we are obtaining the sample from can be assumed normal, and it has a known variance. So our test statistic, z observed, is calculated as x bar minus mu naught over sigma over square root of n, and we know this quantity uses as a reference a normal 0-1 distribution. Now, your calculation of the p-value does depend on whether you are doing a two-sided or a one-sided test. In other words, what your alternative looks like. A two-sided test, meaning your alternative is that mu is not equal to mu naught, the p-value gets evaluated in the following way. Imagine your normal curve as reference, centered at 0, and you now calculate this value, z observed. Could be a positive value, could be a negative value. Regardless, you are going to take the absolute value of that and consider both the negative and the positive of the absolute value. In the two-sided case, your p-value is defined as the area to the left of the negative absolute value plus the area to the right of the positive value. If you want a formula for this, you can calculate the p-value as 2 times the normal CDF at negative of z observed. And this p-value will then just be evaluated against your specified alpha level. Alternatively, if you are doing a one-sided test, in other words, your alternative is of the form either mu is less than mu naught or mu is greater than mu naught, now you have to be a little bit more careful, because now you only want to evaluate the area under your normal curve on one side of the curve. So if you are looking at mu less than mu naught, the implication of that is now you're not taking absolute value of z observed. All you're doing is finding where z observed is, and you want to know what the total area is to the left of that value. In other words, your p-value in this instance is given by the normal CDF at z observed. On the other hand, if your alternative is right-sided, mu greater than mu naught, now when you're looking at your bell curve and you're finding z observed on that curve, you want to know what the area is to the right of that value. We can write a formula down for this as well, but in this instance, our p-value is going to be 1 minus the normal CDF at z observed. So as long as you are able to clearly write down your alternative hypothesis, you know whether it's one or two-sided, you have a formula that you can use to calculate your p-value. Now, let's add another wrinkle to this and add a second case. Again, this parallels the work we did with confidence intervals. So let's assume now in case 2 that the underlying population is not normally distributed. So we do not start with a normal distribution, but we compensate for that by the sample size being large. In this case, you have two different forms that the test statistic can take. And this all depends on whether you know the underlying variance or not. If sigma squared is known, then your test statistic is still going to be z observed equal to x bar minus mu naught over sigma over square root of n. On the other hand, if sigma squared is unknown, you now have to rely on a sample quantity. And the formula for z observed now becomes x bar minus mu naught. And because sigma is unknown, you replace it by s, your sample standard deviation. But that's the only change to the formula. So fundamentally, not a whole lot changes, right? Because we're taking a population quantity that's unknown and replacing it with an estimate from our sample. But in this setting, because we do not have normality, we cannot do an exact calculation. Provided our sample size is large enough, though, we can invoke the central limit theorem, and at least for the purposes of this class, we are going to say sample size large enough means n is at least 30. If that's the case, you can still use the normal 0, 1 as a reference. So all the formulas that we developed for case 1 carry over. The only fundamental change is that we now are doing an approximation based on the central limit theorem, whereas previously we were doing exact calculations. Finally, there is one more scenario of hypothesis testing that we'll consider for today. We are still considering hypotheses with regards to the population mean, but we're introducing a variation to that. So we've covered two different cases. Case 1 where we assume normality and the variance is known. Case 2 where we do not assume normality, but we can use the central limit theorem to do an approximation because our sample size is large. Now we're looking at the third case. We are back to assuming that we have a normal population, but now sigma squared is unknown. So if you've been tracking the parallels to confidence intervals, this should again look familiar. When we start with a normal distribution, but sigma squared is unknown, that is a recipe that lands us in the world of having to use t-distributions. So if you identify you have normality, but sigma squared is unknown, the result is that you're no longer using a z statistic for the test, you're going to use a t statistic. So your test statistic now, t observed, gets calculated as x bar minus mu naught, the value under the null hypothesis, over sample standard deviation divided by square root of n. So fundamentally, the formula has not changed. But because we know that the reference distribution is different, we call it t observed as opposed to previously having called it z observed. Because in this instance, we no longer use the normal distribution as a reference. We now use the t distribution with n-1 degrees of freedom as a reference. And in the live session tomorrow, March 26th, I will talk you through a couple of examples illustrating all these different cases. So not a whole lot changes here, but the formulas have enough of a difference to them that it's worth just writing them down. So let's consider the three ways in which our alternative hypothesis could be formulated. We could have a two-sided alternative that says mu is not equal to mu naught. If you're in this case 3 setting and you want to evaluate your test using a rejection region, the form of your rejection region now is going to be the absolute value of t observed is greater than or equal to the t reference value with area to the right alpha over 2 and n minus 1 degrees of freedom. Similarly, if you're doing a one-sided test and you say mu is less than mu naught, then your rejection region is going to consist of all values t observed less than or equal to the t reference value, negative t reference value with area alpha to the right and n minus 1 degrees of freedom. And finally, if your alternative is that mu is greater than mu naught, then your rejection region is going to be t observed greater than or equal to t of alpha and n minus 1 degrees of freedom. And I am just noticing here, for whatever reason, I was writing null hypothesis, but all of these are alternative hypotheses. So form of the alternative determines what your rejection region looks like. Also, we can write down formulas for the p-value, but this requires defining a new function, or at least thinking in terms of using your calculator. This relies on using the tcdf function on your calculator. Now, using tcdf is going to require specifying 3 different input values, a lower bound and an upper bound. This is equivalent to like lower bound and upper bound when evaluating the normal CDF, but you also have to specify the degrees of freedom. So in the case of a two-sided test, we have the same thing play out as we did in the case 1, case 2 idea where we're using a normal distribution. We want to evaluate on our t-distribution curve both the area to the left of the negative of the observed value and the area to the right of the positive of the observed value. And so the p-value in this instance is given by 2 times the tcdf. Lower bound is negative infinity. Upper bound is negative the absolute value of t observed. And finally, degrees of freedom specified as n minus 1. In the case of a one-sided test, if you have an alternative mu less than mu naught, then your p-value only wants to consider the area on the left. So it will be tcdf, lower bound is negative infinity, upper bound is t observed, and degrees of freedom n minus 1. And finally, if you're looking at the greater than alternative, the other one-sided test, here your p-value is given by tcdf, but now the t observed is your lower bound, and your upper bound is infinity, and degrees of freedom still n minus 1. So again, in tomorrow's video, we will go through some examples of doing this evaluation, both in terms of rejection region and in terms of p-value. When we do delve into this case 3, though, the one thing you can put aside is we're not going to worry too much about evaluating type 2 error, because this is at least a little bit beyond the scope of what we are able to dig into in the time and format that we have left. But if you are following along in the Devore book and you are interested, page references are included here, and you're welcome to go and read about that a little bit. The last thing I'll say in this video is an emphasis of nomenclature, right? Z-test versus t-test, making sure we understand when we're using which name and why we're using that name. If we're in case 1 or in case 2, we are using a z-test because our reference distribution is a normal distribution. In case 3, we're using a t-test because our reference distribution is a t-distribution with n-1 degrees of freedom. But the fundamental of the test statistic is the same, because z observed is x bar minus mu naught over sigma over square root of n, or perhaps if we don't know sigma, we replace it by s. And for t observed, we know that we're using s over square root of n. So it's not an approximation case like sometimes in z observed we can replace sigma by s and know the normal distribution is still an approximation. The t observed statistic is if we have normality, but we don't know the population variance. So the difference in nomenclature, it just tells us which reference distribution to use. So I will leave you with that for today, and I will talk to you tomorrow when we do some examples. Hope everyone is doing well.